So thanks, Emmanuel, for the nice introduction. Because so I will continue with the third channel of the SPICAF instrument, which is called SOIR. And this is a busy slide, but summarize the channel and what he's doing. So this is an infrared E-shell spectrometer associated with a specific, very special filter, which you can see here, which is used to select the wavelength region that will be recorded. So this instrument, in fact, is using the same principle as the Virtis H instrument that was described earlier. It means that you have a certain number of orders which are seen by the instrument and by the detector, and we do it slightly differently than in Virtis H in the fact that first we have this filter to just select normally one order, and then you will see after this is not perfect, and what is recorded by the instrument, in fact, is a summation of different orders. I will come into the details afterwards, but the basic idea of this filter is, in fact, should have been to select the order to record. And this is done by applying a radio frequency on this crystal, and the optics and the characteristics of this crystal are changed by the radio frequency and only let some wavelength pass through the crystal. This means that the selection of the spectral range is done without any moving pieces into the instrument. So what do we do with this instrument? This is a very specific instrument. It does solar occultation measurements. So you have the instrument on board the spacecraft on its orbit, and it's looking at the sun. And when the light goes through the atmosphere, it gets modified by the presence of the components and what's inside the atmosphere, and that's what we are measuring. So we have here the level outside the atmosphere, which is kind of the reference, and all spectra recorded while passing through the atmosphere will be divided by this reference. This was already, this is the same principle as was explained by Emmanuel before. So what we do is we change the frequency which is applied on the filter 4 times per second. And each time we record one spectrum. At the end of this set of measurements, occultation, this is the kind of number of spectra that we record. So those are transmittance. So this divided by the reference, and we have one such transmittance each second for 4 different spectral regions. And you can see here that there are 2 kinds of things that we observe: lines, which are absorption lines due to the constituent inside the atmosphere, and then you have a decrease of the signal, which is due to the aerosols. So this was long, but it's necessary. So basically, this instrument is very simple because it's using transmittances. That's what we provide to you, so you can just download or get the data and directly use them. There is no calibration need. It's not radiometric demanding, but there are still some details that have to be understood with this instrument. And the first one is what are we really recording? And this is illustrated here. So during the occultation, this is the sun, and this is the image of the slit of the instrument position on the sun, and you see that this slit, this is exaggerated. In practice, it's not, the angle is not that large, but the slit is really parallel to the limb only at 60 kilometers, and then it changes slightly with inclination. If we zoom on this, in fact, the slit is divided into two bins. This is due to the limitation on data volume that we can download to the ground. And you have the spatial dimension here and the spectral dimension here. And if you now look at the detector, which is a 2D detector, you have the spatial dimension here and the spectral here. Spectral being composed on 320 pixels, and the two bins are those one. So this is to illustrate that. So we have 4 frequency per second, and in fact, when I said that for each one you had 1 spectrum, in fact you have 2 because we have 2 bins. But that's really a detail. Now the most complicated part of the instrument is the fact that, as I said, the filter was designed to let pass only one order. In practice, this filter, whose bandpass is reproduced here, is larger than one order. So this here, so you have here the spectrum we want to record. Here the lines, the box here, delimits the order which were targeted, but in fact you will have information from 2 or more adjacent orders. In practice, this means that on the detector you will have signal coming from the main order, but signal coming from adjacent orders too, and all those added together to give you this transmittance. So the message here is when you get a transmission from SOIR, all the spikes are real, but not all are at the right wavelength which is indicated here. Okay, so now I will basically describe what we have done, measured, and what has been delivered to the PSA. So when I described the instrument, so I explained how we came to these 8 spectra, so 4 orders and 2 bins. This is the main configuration that we used. Of course, the instrument is more flexible, and we had tested different options, so that's why it's indicated here. And if you want to retrieve data, you have to check in which case you are, but that's details. More important is that we have 2 types of recording, what we call hopping. It means that we choose 4 frequency to be applied to the AOTF, and those 4 frequencies are repeated every 1 second. The other observation that we can do is what we call stepping. It means you give the first frequency and you step through the frequencies. This, I will explain, allows us to make calibration. And then, of course, some indication, we can vary the integration time to optimize the observations, and we do a lot of accumulations to increase the signal-to-noise ratio. So the different modes that we have done through the mission, mainly occultations. Some are called ingress or egress, that's geometry. We have done full scan, so that's, as I described, the stepping mode. So we go through all the orders which are available to the instrument. That means 100 orders, covering the complete sensitive wavelength range. We have tried nadir, but the instrument is not optimized for nadir observations that not really interesting scientifically. And then there are calibration. I go through all these because the type of measurement, which is given here by a one letter, appears in the name of the files. So when you want to find a scientific one, you have to select basically the first 3 lines here. So up to now we have delivered everything to the PSA. Some of the last updates are still being ingested, but everything is there. We delivered what we call PSA level 2, which means raw data, basically with some basic corrections. I will go into some details afterwards. And then level 3, which are the transmissions that you are free to use for you. So I will go very quickly through PSA level 2. This is the kind of things that you will have. You will have a browse, some data on the calibration, and then the data. And a lot of other things that I won't describe. What is interesting here are the data. You see that they follow a very basic naming convention, and in each of those subdirectories you have a series of files containing really the observations, and then files which are which contains information on how the observation has been obtained. Okay, so this is an example of raw data. So it's the spectra that we record, it's not transmittance. In the browse directory, you have such nice plots which give you an indication for the different spectra, so the 2 bins and 4 outer frequencies, an average signal during the occultations. This gives you a direct check that everything was correct. So briefly, how do we process those level 2 into level 3? So first we have to correct for nonlinearities in the detector. Then we have to convert the frequency that we have applied to the AOTF to something that is more meaningful for spectra, which is wave number, to derive the order in which you are working. I have indicated here the 3 main papers in which you can find all the details on the procedures and and the content of the files on the PSA. So the main process that is being done between level 2 and level 3 is, of course, the determination of the transmittance. It seems easy. You have a reference spectra outside the atmosphere, and you have your spectrum within the atmosphere. The intuitive way is just to divide 1 by 1. Of course, it's not that easy. In fact, there were, we think, problem of pointing, and here, this is looking at the sun. This should be normally always the same level, but you see that this is decreasing or increasing. You saw that in the previous example too. So we have to correct for that, and the way we did it was to apply a regression and consider this regression as the reference level. However, we found that in some cases, doing such a simple method gave sometimes strange transmittances, and for example, we got transmittances above 1, which is not possible. So that's what we have done lately. It's to really derive a new way to obtain transmittances in a better manner. And this is a little more complicated, of course. Then I won't enter into the details. I have placed the details on the presentation so that you can go through, but I won't describe that too much. We still use regression, but the regression can be shifted so that we optimize the way it's done. And then we have introduced a check, a supplementary check, to be sure that the transmittances are always below 1. And you see here that we have now a series of criteria that have to be followed. So this is the details. You have them. I won't describe them. This is a kind of examples. So above you have just so let me explain. This is still level 2, so just ADU levels with and this is time. So time during the occultation. There, for example, we just took 4 pixels and look at the intensity on those pixels during the occultation. So this is normally the region where we are looking at the sun. Before, it's just satellite starting to point in the right direction. So here we have sun, and this is really the occultation. And you see that here the regression allows us to derive transmittance which are valid. But sometimes you have that kind of observations, and of course this is meaningful. So we have to remove those. And this is a problem of level of signal. So those are 2 examples which are rejected and never appears in the level 3 data. 2 last things that we have to do is to convert the pixels number to wave number, and we delete the wrong pixels. We remove those crazy pixels, as we call them. Again, we obtain level 3 data, and the structure is about the same. That's just a short description. So you have basically 1 file per occultation per order. And per line, you have all the information corresponding to 1 instant. So with 1 file, you have all the information you need to reconstruct the occultation. You have, of course, description of the timing, geometry, and then the data. You have also at that level calibration, because this is absolutely needed to use the data, and basically those describe the AOTF. So you have the rules how to convert frequency to wave number, and vice versa, the transfer functions, the Blaze functions of the grating, and then an indication of the evolution of the resolution in function of the order. No. So how to access the data? This is the easiest way is to go on our website, and then you will have access to the observation database. I will show you access to the data SOIR repository and some tools. And I will very briefly describe those. We have online an overview files with all the observations that were done, a lot of description and parameters describing the observations. We have an online tool to let you select which observations you are looking for. The link to the repository data, you have two things there, a link to the PSA to help you find your data, and then a direct results of profiles and things that were used for publications. So you saw there were also some tools that were available. I won't go into the details. They allow you to go through the data and have a first look, just to have an impression of what you are downloading. They are still, they will be updated to the latest version that has been downloaded, uploaded to the PSA, but those are tools which allows you to select the order or the latitude, longitude or time, and to let you plot interesting information or even the data. And we have that for level 2 and level 3. Okay, so for example, those are level 2, some of the plots that you can perform with the tool. And when you are using asking level 3, you can plot different things, even housekeeping data if you are interested in that. So those are things. For the higher level data, we are so either posting them on the website I just mentioned. The idea is that in the near future we will post all of them, individual profiles and average one, on the VESPA website, which was already cited by previously. Okay. Okay. The conclusion basically is what I said as a conclusion of the presentation yesterday. There are still a lot of things to do. We have only few IDs. You are free to use the data to test your IDs, and they are there for that. And just to finish, this is the list and the contact of the person of the team. If you have any questions or trouble to access the data or want to be helped, please you contact us.